The cosmos holds a secret we are desperate to solve. For all of human history, we have gazed at the stars and asked one profound question: are we alone in this immense universe? That question is no longer just a dream. It is a scientific quest, a thrilling hunt across the galaxy for signs of another living world, and we are closer than ever to finding an answer. By the end of this journey, you will know the 25 most promising cosmic wonders where alien life could be hiding right now. We will travel to moons with hidden oceans, planets of diamond and tar, and even consider life floating in the clouds of a hellish world. What does it truly mean for a place to be alive? The first candidate on our list is not a planet at all, but a moon. Orbiting the giant Jupiter, Europa presents a world of contradictions. Its surface is a frozen, fractured shell, crisscrossed with long, dark lines and ridges that look like a giant cracked egg. This ice is remarkably smooth, with very few craters, which tells scientists something incredible. That surface is young and constantly being renewed, hinting at a powerful, hidden force beneath the ice, and that force is a global ocean. Europa is not just a ball of ice. It contains more liquid water than all of Earth's oceans combined, locked beneath an icy crust that might be only a few miles thick in places. The question is, what keeps this immense sea from freezing solid in the cold depths of space? The answer lies with its parent planet, Jupiter. The immense gravity of the gas giant constantly squeezes and stretches Europa as it orbits. This gravitational tug-of-war, called tidal heating, generates enough warmth from the moon's very core to keep that global ocean in a liquid state. This means Europa has two of life's fundamental requirements: liquid water and a source of energy. But where could life gain a foothold in that dark, sunless sea? The most promising answer lies on the seafloor. Scientists strongly suspect that on the ocean bottom, heated by Europa's core, there are hydrothermal vents, just like the ones we find in Earth's deepest oceans. On our planet, these vents are oases of life, supporting entire ecosystems of bizarre creatures that thrive on chemical energy, completely independent of sunlight. If similar vents exist on Europa, they could provide the perfect chemistry and energy for microbial life to emerge and survive. It is a profound thought. While we look for life on the surface of Mars, one of the most promising places in our entire solar system for life, as we know it, could be swimming in a dark, salty ocean over 400 million miles away. Europa's hidden sea is not the only one. Saturn's small, icy moon Enceladus has made an even more dramatic statement about its potential for life. It did not wait for us to drill through its ice. It shouted its secrets directly into space. For decades, Enceladus appeared as little more than a bright, reflective speck in Saturn's rings, the most reflective object in our entire solar system. But when the Cassini spacecraft arrived at Saturn, it saw something that changed everything. Cassini captured stunning images of gigantic geysers, colossal plumes of water vapor and ice crystals, erupting into space from deep fissures near the moon's south pole. These were not mere wisps, they were towering fountains jetting hundreds of miles above the surface, backlit by the sun in a breathtaking display of cosmic activity. This was not a dormant world. This was a moon actively venting its internal ocean into the void. Those plumes are our golden ticket. They are direct, untainted samples from the salty ocean that sloshes beneath Enceladus's icy crust, and Cassini flew right through them. The spacecraft's instruments tasted those particles, and the results were staggering. They found simple organic molecules, the carbon-rich building blocks necessary for life as we know it. They detected tiny silica nanoparticles, a strong chemical fingerprint that points to hot water interacting with rock on the ocean floor. In other words, Enceladus almost certainly has hydrothermal vents just like Europa. But the most tantalizing discovery of all was molecular hydrogen. This gas is like a high-energy snack for certain types of microbes. On Earth, in the darkness around hydrothermal vents, some of the most ancient life forms use hydrogen combined with carbon dioxide to produce the energy they need to survive. This process is called chemosynthesis. The presence of molecular hydrogen in Enceladus's plumes means its hidden ocean could be providing not just water and organics, but a readily available food source. Enceladus presents us with a checklist for habitability, a global subsurface ocean check, a source of chemical energy from hydrothermal activity check. The right chemistry, including salts and organic molecules check. It has handed us on a silver platter evidence that its dark waters could be a cozy home for microbial life. We did not have to land, we did not have to dig. The moon itself offered us a taste of its ocean, and the flavor was promisingly familiar. Yet for all the promise of these distant moons, we cannot ignore the world next door. Mars has transformed in our eyes from a simple red dot to a complex, haunting landscape that whispers of a wetter, warmer past. Its surface is a museum of ancient water. Orbital images reveal vast, dried-up river valleys that snake across the plains, wider than the Grand Canyon. We see the ghostly outlines of enormous lake beds and deltas, sedimentary layers that could only have been laid down by persistent standing water. These features tell a story of a Mars that was profoundly different billions of years ago, a world wrapped in a thicker atmosphere that allowed rivers to flow and lakes to pool. This was a time when life could have first sparked on our own planet. If it happened here on Earth, why not there, in those ancient Martian streams? But the story does not end in the distant past. Modern Mars continues to surprise us with hints of activity. From orbit, scientists have observed mysterious, dark streaks that appear on sun-facing crater walls during the warmer seasons. They are called recurring slope lineae, and they look for all the world like damp patches, as if briny water is seeping just below the surface before evaporating away. Even more compelling is the evidence from beneath the ground. Radar data from a European orbiter has detected what appear to be pockets of liquid water, subsurface lakes, trapped under the ice of the South Polar region. These could be incredibly salty, cold brines, but they are liquid nonetheless. Then there is the tantalizing mystery of the methane. On Earth, the vast majority of methane in our atmosphere is produced by living organisms. On Mars, rovers and orbiters have detected sporadic, unexplained spikes of this gas. It could be the product of subsurface geology, a simple chemical reaction between rocks and water. Or it could be a metabolic byproduct from microbial life hidden deep underground, a faint chemical signature seeping up through the soil. We simply do not know. This is why our robotic explorers are there right now. Rovers like Perseverance are not just taking pictures, they are active detectives. They drill into promising rocks, ones that formed in that ancient lake in Jezero crater, carefully sealing samples for a future mission to bring back to Earth. They analyze the chemistry of the air and soil, listening for any whisper the planet might offer. Every panorama of rust-colored dunes and jagged hills is a clue in the greatest cold case in the solar system. Mars is no longer just a barren neighbor. It is a puzzle box, and we are patiently working to pry it open, searching for a sign that we were never truly alone in this corner of the cosmos. While Mars whispers of a lost past, one world in our solar system presents a vibrant, alien present. Saturn's largest moon, Titan, is a place of stunning and eerie familiarity. It is the only moon in our solar system with a substantial atmosphere, a thick, hazy orange shroud of nitrogen and methane that hides its surface from prying eyes. For years, that surface was a complete mystery until the Cassini spacecraft and its Huygens lander pierced the veil. What they revealed was a landscape that looked hauntingly like home, yet was built from entirely different materials. Titan has rolling sand dunes, vast plains, and even weather, but its rivers are not carved by water. They are carved by liquid methane and ethane. Its lakes are not filled with water, but with these same hydrocarbons, forming eerie, mirror-smooth bodies of liquid that pool in polar depressions. Here it rains methane, filling streams that flow into hydrocarbon seas. It is a world with a full, active hydrological cycle, just like Earth's, but operating at a bone-chilling -180 degrees Celsius. Water here is as hard as rock, acting as the bedrock for this alien geology. This raises a profound question. Could a world this chemically rich and dynamic, yet so bitterly cold, ever give rise to life? The answer might lie in a radical shift in our thinking. Life as we know it requires liquid water, but life as we do not know it might not. Titan is awash in complex organic chemistry. Its atmosphere is a giant chemical factory where sunlight breaks apart methane and nitrogen molecules, allowing them to recombine into more complex organic compounds like acetylene and hydrogen cyanide. These molecules clump together into haze particles and slowly drift down like snow to coat the surface. This constant organic rain has likely been falling for billions of years, creating layers of organic sludge that could be tens of meters thick. In this bizarre environment, could a different kind of life have emerged? Astrobiologists call it cryolife, life that thrives in extreme cold. Instead of using water as its internal solvent, such life might use liquid methane or ethane. Its cell membranes would not be made of lipids, but of sturdier, more flexible compounds that can remain functional in the deep freeze. Its metabolism would be based on consuming acetylene or hydrogen, breathing hydrogen instead of oxygen. It would be a form of life with a biochemistry fundamentally alien to our own, a shadow biosphere operating on rules we are only beginning to guess. To explore this possibility, we are sending a revolutionary mission. The Dragonfly rotorcraft, set to launch in the late 2020s, is not a rover. It is a drone designed to fly through Titan's thick atmosphere, which makes flight remarkably easy. Dragonfly will leapfrog across the Moon's surface, sampling the organic rich sands near the ancient dunes and finally landing in the Selk impact crater, a site where water and organics may have mixed in a warm, wet past. It will search for chemical biosignatures, the fingerprints of this exotic cryolife. Titan stands as a powerful reminder that our search for life must be broad. We cannot only look for pale reflections of Earth. We must be prepared to find something utterly strange, something that breathes a different air and swims in different seas, thriving in a cold, golden haze under the ringed light of Saturn. Yet, even as we consider life on frozen moons, a far more hostile world demands our attention. Venus is Earth's twisted twin, a stark warning of the runaway greenhouse effect. Its surface is a true hellscape, crushed under an atmosphere 90 times thicker than our own, with temperatures hot enough to melt lead and clouds of sulfuric acid raining down. It seems the last place anyone would look for life, but look up, about 50 kilometers above that scorching surface, something remarkable happens. The temperature and pressure in Venus's cloud decks become startlingly Earth-like. You could walk outside in a protective suit and feel a comfortable room temperature with pressure similar to sea level on Earth. Within this temperate band in an otherwise lethal sky, scientists have proposed a breathtaking possibility. Could life exist there, not on the surface but floating high in the clouds? The idea of an aerial biosphere is not pure fantasy. On Earth, we find hardy microbes drifting in our own upper atmosphere, surviving on dust and moisture. On Venus, such life would need to be incredibly resilient, adapted to a highly acidic environment, perhaps living inside protective shells within the sulfuric acid droplets themselves. The cloud decks could provide everything microbes might need: sunlight, chemical nutrients from the atmosphere, and even traces of water vapor. Then came the bombshell announcement. In 2020, a team of astronomers reported detecting phosphine gas in Venus's clouds. On Earth, phosphine is a gas almost exclusively made by industrial processes or by anaerobic microbes thriving in oxygen-free environments like swamps and animal guts. Finding it on a rocky planet was shocking, as there are no known geological processes on Venus that should produce it in such quantities. It was a potential biosignature, a chemical hint of life hanging in the alien sky. The discovery ignited fierce debate and immediate follow-up studies, with some teams failing to detect the signal and others standing by their original analysis. The truth is, we simply do not know what is happening in those shrouded clouds. This profound uncertainty is why Venus is back in the spotlight. New missions are being prepared to probe its secrets. NASA Da Vinci I+ mission will send a probe plunging through the atmosphere, sampling its chemistry layer by layer to hunt for organic molecules and map the terrain below. The Veritas orbiter will use radar to pierce the clouds and map the surface in exquisite detail, searching for clues about Venus's volcanic past and whether it ever had oceans. They aim to answer whether this world of acid and heat could host a floating, aerial ecosystem, a testament to life's ability to find a foothold in the most unexpected corners of the cosmos. 40 light-years from our solar system, a quiet, dim red star hosts a planetary family unlike any other we have found. The TRAPPIST-1 system is a cosmic jackpot, a single star orbited by 7 rocky worlds, each one roughly the size of Earth or a little smaller. Most stars might have 1 or 2 planets in their habitable zone, the region where temperatures could allow for liquid water. TRAPPIST-1 has 3. Planets E, F, and G all circle firmly within that temperate band around their cool, small sun. This means we are not looking at just one potential oasis, but a trio of neighboring worlds where conditions might be just right for oceans to form. The sheer density of opportunity here is staggering. Picture our own solar system with vast, empty stretches between planets. Now, compress that entire family into a space smaller than the orbit of Mercury around our Sun. In the TRAPPIST-1 system, the planets are incredibly close together. If you stood on the surface of one of these worlds, the neighboring planets would not be mere points of light. They would dominate the sky, appearing as large as our own moon or even bigger, their cloud patterns and surface features visible to the naked eye in a breathtaking celestial dance. This proximity creates fascinating possibilities. Gravitational tugs between the planets could provide a source of internal heat through tidal forces, much like Jupiter does for Europa, potentially keeping their geologic engines running and their subsurface water liquid. But such a tight orbit around a small, cool star comes with a significant caveat. These planets are likely tidally locked, meaning one side permanently faces the star in eternal daylight, while the other is locked in perpetual night. This sounds like a recipe for extremes, a scorching hot day side and a frozen dark side. Yet, if these worlds possess substantial atmospheres, winds could circulate heat around the planet, creating a more temperate twilight zone along the terminator line between day and night. This is where life could find a precarious but possible foothold in a land of eternal sunrise or sunset. The ultimate question for TRAPPIST-1 is about air. Do any of these Earth-sized worlds hold onto a life-sustaining atmosphere, or have they been stripped bare by the radiation from their red dwarf star, which can be prone to violent flares? Our next generation of telescopes, like the James Webb Space Telescope, is designed to answer this very question. By analyzing the starlight that filters through a planet's atmosphere as it transits across the face of its star, Webb can search for the chemical fingerprints of water vapor, methane, carbon dioxide, and even oxygen. Finding the right combination of gases could transform these distant dots of light from intriguing possibilities into our best candidates for a living world beyond our solar system. The TRAPPIST-1 system is a reminder that sometimes the universe concentrates its wonders, offering not just one chance, but a whole family of chances hanging together in the dark. But distance alone does not guarantee a welcoming home. Our nearest stellar neighbor, Proxima Centauri, is a faint red dwarf star, and orbiting it is a world that has captivated our imagination simply by being so close. Proxima Centauri b is a rocky planet, a little more massive than Earth, and it sits squarely within its star's habitable zone. At just over 4 light-years away, it is the closest known exoplanet to our solar system, a cosmic stone's throw in the grand scheme of the galaxy. This proximity makes it more than just a scientific target. It feels like a tangible destination, the first port of call in humanity's future journey to the stars. Yet, a world this close to such a star faces extraordinary challenges. Proxima Centauri b is almost certainly tidally locked, with one hemisphere in permanent, scorching daylight and the other in endless, frozen night. This could create a planet of extremes, but as with the TRAPPIST worlds, a substantial atmosphere could ferry warmth around the globe, potentially creating a narrow, livable band along the twilight line. The greater threat comes from the star itself. Red dwarfs like Proxima Centauri are notoriously tempestuous, frequently erupting in massive stellar flares that blast out torrents of ultraviolet and X-ray radiation. For life to survive on the surface of Proxima b, it would need a formidable shield, a thick, protective atmosphere, or a powerful global magnetic field like Earth's would be essential to deflect this relentless stellar fury and prevent the planet's surface from being sterilized. Does it have these defenses? We simply do not know. The tantalizing possibility that it might has inspired one of the most audacious concepts in space exploration, breakthrough starshot. The idea is to send a fleet of tiny, gram-scale spacecraft, each attached to a light sail, to this neighboring star. From Earth, a powerful array of lasers would blast these sails, accelerating them to an incredible 20% the speed of light. At that pace, the journey would take just over 20 years. These nanocraft would then zip past the Proxima Centauri system in a matter of hours, snapping pictures and collecting data as they fly by, beaming the information back to Earth. It is a mission that sounds like science fiction, yet it is based on real physics and represents our deepest desire to reach out and touch another world directly. For now, Proxima b remains a blurry dot in our telescopes, a world of profound questions. Is it a blasted, airless rock scoured clean by stellar winds? Or is it a sheltered oasis with deep oceans huddled on its dark side, or beneath a global ice cap protecting a fragile biosphere? It is the ultimate nearby mystery, a reminder that the frontier of life may begin right on our cosmic doorstep. The search for a world truly like our own took a giant leap forward with the discovery of Kepler 452b. This planet, orbiting a star remarkably similar to our Sun, earned the nickname Earth's cousin for good reason. It was found by the Kepler Space Telescope, which stared at a single patch of sky for years, watching for the telltale dimming of starlight as planets crossed in front of their suns. The data revealed a world about 60% larger than Earth, circling its star in a 385-day year, a rhythm almost identical to our own. But the most profound detail is its location. Kepler 452b sits firmly within its star's habitable zone, the region where liquid water could exist on a rocky surface. And it has been sitting there for a staggering 6 billion years. That is 1.5 billion years longer than Earth has existed in our own sun's habitable zone. This timeline is a game changer. Think about the story of life on our planet. It took roughly 1 billion years for the first simple cells to emerge in Earth's ancient oceans. It took another 2 billion for complex multicellular life to evolve, and it was only in the last sliver of time that intelligence and technology arose. Kepler 452b has had an extra 1.5 billion years of stable, temperate conditions. If life began there even at a similar pace to Earth, it has had an unimaginable head start. What kind of civilizations might have risen and fallen in that vast expanse of time? What technologies could have been mastered? The potential is both thrilling and deeply humbling. Yet for all the hope this world inspires, a critical uncertainty remains. Is Kepler 452b truly a rocky super-Earth, a larger version of our own planet, or is it a mini Neptune, a gaseous world with no solid surface to walk on? The Kepler telescope could tell us the planet's size and orbit, but not its composition. The data shows a clear, repeating dip in starlight, a graph that confirms its presence and period, but the true nature of the world is hidden. This is the frontier of exoplanet science. We are finding these tantalizing dots of light, these echoes of other worlds, and we must then piece together their stories from faint clues. Future telescopes will analyze the starlight filtering through this planet's atmosphere, if it has one, searching for the chemical signatures of water, oxygen, and industrial pollutants. For now, Kepler 452b stands as a symbol of a profound cosmic possibility. It is a reminder that Earth may not be a unique accident, but one example of a common template, a world with ample time for the quiet, patient experiment of life to unfold into something extraordinary. Some worlds are not simply rocky or gaseous, but something in between, a strange hybrid that defies our familiar categories. GJ1214b is one of these enigmatic places, a super-Earth that may be less of a planet and more of a planet-wide ocean. Discovered orbiting a dim red dwarf star about 40 light-years away, this world is about 2.5 times the size of Earth and nearly 7 times as massive. That critical ratio, its mass to its size, tells scientists something profound. It is far too light to be a rocky world like our own, and yet too dense to be a puffy gas giant like Neptune. The most compelling explanation is that a huge fraction of its bulk is not rock or gas but water. Imagine a world where the very structure is built around a deep, global ocean, perhaps hundreds of kilometers deep, covering the entire surface. This would not be an ocean as we know it. At the bottom, where this unimaginable volume of water meets the planet's rocky core, the pressure would be so immense that the water would be compressed into exotic forms of ice, not cold ice, but hot ice, solid because of the crushing pressure rather than the temperature. Above this strange, slushy seafloor, a liquid ocean of staggering depth would stretch upward, completely enveloping the world. There would be no continents, no islands, not a single speck of land anywhere. The sky above this endless sea would be a perpetual, oppressive blanket. GJ1214b is wrapped in a thick, steamy atmosphere of hydrogen and helium, a primordial shroud that traps heat and creates a permanent, superheated greenhouse effect. Surface temperatures could soar to hundreds of degrees. In this environment, the very concept of a surface blurs. The atmosphere would gradually thicken into a hot, dense vapor, which would then condense into that planet-wide, high-pressure ocean. So, could life exist in such a place? It is a staggering thought. Any organism here would need to thrive in total darkness beneath a crushing weight of water, in temperatures that would boil a kettle on Earth, and without any mineral surface to cling to. Yet in our own oceans, we find life at hydrothermal vents, independent of sunlight, fueled by chemistry. If the rocky core of GJ1214b is geologically active, it could be peppered with such vents, spewing minerals and heat into that dark global abyss. Life here would be truly alien, perhaps floating in the deep currents or drifting in vast, eternal night, never knowing a sun or a shore. We have learned about this world's strange atmosphere through a technique called transmission spectroscopy. When GJ1214b passes in front of its star, a tiny fraction of the starlight filters through the planet's atmospheric rim. By analyzing that filtered light, astronomers can detect which wavelengths are absorbed, revealing the fingerprints of different gases. The data shows a flat, featureless spectrum, which is itself a clue. It suggests an atmosphere that is either very hazy, like Titan's, or incredibly dense and steamy, perfectly consistent with a world shrouded in hot water vapor. This makes GJ1214b a cosmic chimera, a water world that is both a tantalizing possibility and a forbidding mystery, a reminder that life, if it is truly tenacious, may find a way in the most profound and pressurized depths imaginable. The search for a stable home around a turbulent star leads us to another remarkable world, LHS 1140b. While many red dwarfs are prone to violent flares that can strip away a planet's atmosphere, this super-Earth orbits a far more gentle sun. Its star, LHS 1140, is unusually quiet and calm for its type, offering a rare sanctuary in the chaos. This world is about 1.7 times the size of Earth and over 6 times as massive, making it incredibly dense. That density is the first clue that we are looking at a solid, rocky planet, likely with a large iron core, not a puffy gas ball. It completes an orbit every 25 days, placing it squarely within the star's habitable zone, the temperate region where water could be liquid. But the most exciting possibility comes from what might surround that rocky body. Recent observations suggest LHS 1140b could be something extraordinary, a Hycean world. This term blends hydrogen and ocean, describing a planet with a thick, hydrogen-rich atmosphere blanketing a global, planet-wide sea. Picture a world with no land in sight, only endless ocean under a pinkish, hazy sky lit by a dim red sun. The hydrogen atmosphere would act as a massive insulator, trapping heat and potentially keeping that global ocean liquid even far from its star. This combination makes it a prime candidate in the hunt for life. A global ocean provides a vast, connected medium for chemistry to play out, and a thick atmosphere offers protection from space radiation. The James Webb Space Telescope has already turned its gaze toward this promising world. Its powerful instruments are analyzing the starlight that filters through the planet's atmosphere during its transits, searching for the chemical fingerprints of water vapor, methane, and other molecules that could hint at biological activity. Finding the right mix of gases here could provide our first strong evidence of a habitable environment, and perhaps even a living one on a world beyond our solar system. LHS 1140b represents a new class of hope, a world that may have held onto its protective shroud and its life-giving waters for billions of years, waiting silently in the light of a quiet star. Our search for life has so far focused on individual worlds, but perhaps we need to pull the camera back, far back, to see the bigger picture. The cosmic address of a planet may be just as important as its atmosphere or oceans. This brings us to the grandest scale of habitability yet, the Galactic Habitable Zone. This is not a place but a region, a kind of cosmic sweet spot within a spiral galaxy like our own Milky Way. To understand it, think of a galaxy as a city of stars with neighborhoods that vary dramatically in safety and opportunity. The inner city, the galactic core, is a dazzling but dangerous metropolis. Stars are packed tightly together, creating a radiant sky but also a perilous environment. Here, the risk of nearby supernova explosions is high. These stellar cataclysms can flood entire star systems with lethal radiation, sterilizing planets and stripping away atmospheres. It is a brilliant, chaotic, and ultimately hostile place for delicate, complex life. On the other extreme, the outer suburbs of a galaxy, the sparse spiral arms and the halo, are quiet, perhaps too quiet. These regions formed early in the universe's history and are dominated by ancient population-2 stars. These stars are metal-poor, meaning they contain very low amounts of elements heavier than hydrogen and helium. Those heavy elements, forged in the hearts of earlier generations of stars, are the essential building blocks for rocky planets like Earth. Without a rich supply of these metals, a star system may form only gas giants or barren, rocky cores too small to hold an atmosphere. Life as we know it needs a rocky platform, and that requires a certain cosmic wealth. The Galactic Habitable Zone is the ring-shaped region between these two extremes. It is far enough from the violent core to avoid frequent sterilizing events, yet close enough to the galactic center to be enriched with those vital heavy elements from previous stellar generations. Within this annular band, stars like our Sun can form with the right mix of materials to build terrestrial planets, and those planets can enjoy long periods of relative peace, billions of years of stable evolution without being wiped clean by a galactic catastrophe. Our own solar system resides in a rather unremarkable part of this zone, about halfway out along the Orion Spur, a minor spiral arm. We are not in the thick of things, nor are we out in the lonely frontier. We are in the galactic equivalent of a quiet, well-established suburb with access to good materials and a low crime rate. This concept fundamentally guides our search. It tells us where to point our telescopes with the most hope. When we survey the galaxy for potentially habitable worlds, we can prioritize star systems that share our fortunate cosmic zip code. We should focus our efforts on Sun-like stars orbiting within this temperate ring of the Milky Way and of other spiral galaxies we observe. It is a sobering filter. It suggests that vast swaths of any galaxy, the dazzling core and the impoverished outskirts, may be cosmic dead ends for advanced life. The search for intelligence, then, becomes a hunt within a specific neighborhood, a narrowing of the infinite down to a ring of possibility spinning silently in the dark. But even within that galactic sweet spot, not all worlds enjoy the warmth of a sun. Our next candidate shatters the most basic assumption of habitability, that life needs a star. These are rogue planets, cosmic orphans cast out from their birth systems by gravitational chaos. Picture a world like Jupiter or Earth, but untethered, sailing alone through the infinite cold between the stars. It is a profoundly lonely image, a dark sphere against the backdrop of the Milky Way, with no sunrise, no sunset, only the eternal night of deep space. At first glance, this seems like the ultimate dead end, a frozen tomb drifting in the void. Yet against all odds, these wandering worlds could be cradles for life. The key lies not on their surfaces, which would be frozen wastelands, but deep within. If a rogue planet is large enough and retains enough internal heat from its violent formation, that warmth could persist for billions of years. This heat comes from two main sources. The first is the slow, steady decay of radioactive elements in its core, the same process that helps keep Earth's interior molten. The second, more surprising source could be a large moon. If a planet was ejected with a sizable companion, the gravitational tug of war between them would generate tidal heating, just as Jupiter heats Europa. This constant flexing could provide enough energy to maintain a vast global ocean trapped beneath a thick crust of ice, insulating it from the cold of space. Even more remarkably, some rogue planets could hold onto thick atmospheres, primarily hydrogen, captured during their formation. Hydrogen is an incredibly efficient insulator. Such an atmosphere would act like a cosmic down comforter, trapping the planet's own geothermal heat and preventing it from escaping into space. This could create a relatively stable, though dark and surface-frozen, environment. Now, imagine what life might be like in such a place. Any ecosystem would exist in total, unending darkness, cut off from the energy of any star. But we already know of life on Earth that thrives in such conditions, clustered around hydrothermal vents on the ocean floor. On a rogue planet, these vents, driven by the world's internal heat, could be the only oases in a lightless sea. Life here would be chemosynthetic, feeding on the minerals and chemicals spewing from the planet's interior. In the absolute black, evolution might favor bioluminescence, with organisms generating their own eerie light for communication, hunting, or attraction. The ocean floor could be lit by living constellations, a silent, slow dance of light in a sea that has never known a sun. The concept is staggering, a biosphere that exists entirely independent of any star, a closed loop of energy flowing from a planet's heart to life in its abyss. Rogue planets challenge our very definition of a home. They suggest that life may not be a rare flame clinging to a star, but a hidden spark that can travel the galaxy alone, carrying its own warmth and light into the deepest dark. Floating between the categories of planet and star, there exists a class of cosmic misfits with astonishing potential. Brown dwarfs are the universe's failed stars, objects with dozens of times the mass of Jupiter, yet still too lightweight to ignite the sustained nuclear fusion that powers true stars. They are born from collapsing clouds of gas like stars, but they simply lack the furnace to truly shine. Instead, they glow with a dim, deep red or infrared heat left over from their violent formation, slowly cooling over eons. To stand on a solid surface, if one even exists deep within, would be impossible under crushing gravity and searing heat. Yet, the true promise for life lies not on a surface but in the sky. These objects possess incredibly deep, complex atmospheres, layered like an onion. Within these swirling veils of hydrogen, helium, and exotic compounds, scientists have identified something remarkable: bands where water can exist as liquid droplets forming clouds. Other layers might have clouds of molten iron or sand, creating unimaginable weather patterns driven by fierce winds. This structure leads to a radical idea: the habitable zone could be a floating band within the atmosphere itself. At a specific altitude in a brown dwarf's thick air, the temperature and pressure might be just right, stable and temperate for liquid water to exist in droplets. In this permanent, planet-wide sky, free-floating microbial life could theoretically thrive. These microbes would need to be incredibly resilient, perhaps living inside protective shells within the water droplets, harvesting energy from the chemical gradients in the atmosphere or from the faint infrared glow of the dwarf below. They would form an aerial biosphere, a permanent global ecosystem adrift in an endless twilight. The most compelling argument for life here is time. While stars like our Sun have lifespans of about 10 billion years, a brown dwarf cooling slowly could remain warm for trillions of years. That is 1,000 times longer than the current age of the universe. This offers an almost incomprehensible timeline for the slow, patient chemistry of life to experiment, arise, and evolve. Imagine a biosphere that has had 1 trillion years to perfect itself, a thought that dwarfs human history. Our telescopes, particularly those sensitive to infrared light, have begun to map these strange atmospheres. We see their patchy, dynamic cloud tops and measure their compositions. While we have no direct evidence for life, the theoretical framework is sound: a stable, wet, energy-rich environment that persists for epochs longer than any star. Brown dwarfs challenge us to think of life not as a surface phenomenon, but as a sky-born one, a permanent passenger in the immense, slow fade of a failed star. Yet the story of a world does not always end at its own horizon. Around gas giants in distant solar systems, entire new chapters of possibility may be written in the light of alien suns. Our 14th cosmic wonder is not a planet at all, but the moon of one. Exomoons orbiting giant exoplanets could secretly be the galaxy's most promising homes for life. We have already seen the blueprint right here in our own backyard. Europa and Enceladus taught us that a moon, warmed not by a distant star but by the gravitational embrace of its planet, can harbor vast, life-giving oceans beneath a shell of ice. Now stretch that concept across light years. Imagine a Jupiter-sized world, a behemoth of swirling gas, orbiting comfortably within its star's habitable zone. And circling that giant is a rocky moon, large as Mars or even Earth. This moon would receive a double dose of energy. First, a faint warmth from the distant sun. But more importantly, a powerful internal heat generated by the constant gravitational tug of war with its massive host. This tidal heating could keep a global subsurface ocean liquid for billions of years, just as it does on Europa. But an exomoon might have an even greater advantage: a planetary bodyguard. A giant planet like Jupiter possesses a powerful magnetic field, a vast, invisible shield that deflects harmful cosmic and stellar radiation. A moon orbiting within that protective magnetic bubble would be sheltered from the worst space weather. especially if it orbits a red dwarf star prone to violent flares. Its atmosphere, if it has one, would be safer from being stripped away. This combination is powerful, a hidden ocean fueled by tidal forces, wrapped in a protective magnetic cocoon. The challenge, of course, is seeing them. Detecting an exoplanet is difficult enough, like spotting a firefly crossing a searchlight from 1,000 miles away. Detecting an exomoon is like trying to see that firefly's own tiny companion. It pushes our telescopes to their absolute limits. We look for subtle wobbles in a planet's transit, a slight dimming of starlight that lasts a little longer, or a tiny timing shift in the planet's orbit, all hints of an unseen gravitational dance. And the possibilities grow even stranger. Some theories suggest that large exomoons could themselves have smaller moons, whimsically called moons. Picture the vista from such a place. You stand on the frozen, cracked surface of a worldlet, its horizon sharp and close. Dominating your sky is not a sun, but the colossal, banded sphere of your host planet, filling half the heavens with storms the size of continents. Beyond that, your system's true sun, a small, brilliant disk, rises and sets behind the planet's limb. In that gentle tidal warmth and planetary shelter beneath your feet, an entire alien sea might churn, waiting in the dark. The search for exomoons forces us to widen our gaze. We must learn to look not just for solitary Earths, but for entire families of worlds, where the most habitable real estate might not be the primary planet, but its silent, orbiting companion. The data from a distant, steamy world has just rewritten the rules of our search. 120 light-years away, orbiting a cool red dwarf star, the exoplanet K218b has become a focal point of cosmic intrigue. It is a super-Earth about 8.6 times the mass of our planet, and it resides squarely within its star's habitable zone. But it is what surrounds this world that has astronomers buzzing with possibility. Recent observations from the James Webb Space Telescope have peered into its atmosphere and found a chemical profile unlike any other. Webb's powerful instruments detected the clear signatures of methane and carbon dioxide, and intriguingly, a hint of water vapor. This combination of gases in a hydrogen-rich atmosphere is precisely what scientists predicted for a new class of planet, a Hycean world. The term blends hydrogen and ocean, and it describes a planet utterly alien to our experience. Imagine a world with no continents, no mountains, no dry land of any kind. Instead, a global, planet-wide ocean stretches from pole to pole, its surface heated to perhaps dozens of degrees Celsius. And above this endless sea hangs a thick, extended atmosphere, not of nitrogen and oxygen like ours, but primarily of hydrogen. This shroud acts as a colossal insulator, trapping the star's warmth and maintaining a steamy, stable climate over the entire globe. The conditions on the surface would be extreme, with pressures dozens of times greater than Earth's at sea level, but the ocean itself, shielded by that atmosphere, could remain liquid. This is the Hycean hypothesis, and K218b is our first strong candidate, but the story took an even more dramatic turn. In the same spectroscopic data, scientists identified a tentative, unconfirmed signal that could be dimethyl sulfide. On Earth, this molecule is only produced by life, specifically by marine phytoplankton and some microbes in wetlands. It is not something geology typically makes. Finding it in the atmosphere of another world would be, quite simply, the most profound discovery in human history. The team was careful to stress this is not a detection, but a hint, a whisper in the data that requires much more observation to confirm or refute. Yet its mere possibility has ignited the imagination. Why are Hycean worlds like K218b so important to the hunt? First, they may be incredibly common. Red dwarf stars, the most numerous type in our galaxy, seem to frequently form these larger, mini-Neptune or super-Earth-sized planets. Their thick, puffy atmospheres are easier for our telescopes to analyze than the thin, Earth-like air of smaller rocky worlds. When such a planet transits its star, more starlight filters through its deep atmospheric blanket, giving instruments like Webb a clearer chemical fingerprint to read. They are, in essence, bigger, puffier targets. Second, their very structure might favor the preservation of biosignatures. On a Hycean world, any biological activity in the global ocean would produce gases that could percolate up into that hydrogen-rich atmosphere and become trapped. The lack of a solid surface with weathering rocks and complex geology means there are fewer non-biological processes to confuse the signal. A molecule like dimethyl sulfide, if it is there, would stand out like a beacon. The data from Webb is presented as a graph, a spectrum, where the light from the star is broken into a rainbow, where specific molecules in the planet's atmosphere absorb that light. Deep, narrow valleys appear in the graph. For K2-18b, those valleys line up perfectly with the expected absorption lines for methane, carbon dioxide, and water vapor. It is a visual fingerprint of another world's air. The potential dimethyl sulfide signal is a much smaller, subtler dip in the data, one that future observations will scrutinize. For now, K2-18b stands as a testament to a new direction in astrobiology. We are no longer just looking for pale blue dots. We are searching for steamy, hydrogen-shrouded ocean worlds where life, if it exists, might flourish not on continents, but in a planet-wide, pressurized sea under a pinkish sky. The galaxy holds worlds that defy every notion of a gentle, life-giving star. Orbiting the super-dense, rapidly spinning corpses of exploded stars are the ultimate survivors, pulsar planets. These worlds exist in the most extreme environment we can conceive, bathed not in warm sunlight, but in torrents of deadly radiation and gravitational fury. The very first exoplanets ever discovered back in 1992 were not found around a sun-like star, but around a pulsar designated PSRB 1257+12. This pulsar is a neutron star, the collapsed core of a massive star that died in a supernova, and it spins hundreds of times every second, sweeping the cosmos with a lighthouse-like beam of X-rays and radio waves. That 3 planets were found in this graveyard was a shock. It meant planets could form from the ashes of stellar destruction, or perhaps were the remnants of worlds that somehow survived the apocalyptic blast. The surface conditions on such a world are the stuff of nightmares. It would be scoured by the pulsar's relentless particle wind and lethal X-ray beams, its landscape likely a barren, irradiated wasteland under a perpetual flickering sky. Yet the tenacity of life is a concept we are constantly revising. Could anything persist here? The only conceivable refuge would be deep, deep underground or beneath miles of solid ice. A thick crust, perhaps dozens of kilometers thick, could provide a shield against the radiation bath from above. Within that protective shell, internal heat from the planet's own radioactive elements, or even tidal heating from the pulsar's immense gravity, could maintain a subsurface ocean, a hidden pocket of liquid water isolated from the hellscape above. This leads to an even more radical thought. In an environment so saturated with high-energy particles, perhaps life would not rely on the relatively gentle reactions of organic chemistry at all. What if, instead, it was based on nuclear chemistry? Organisms might harness the constant flux of radiation, using it to power their metabolism directly, their cellular structures built from exotic, radiation-resistant materials unknown on Earth. They would be life forms of pure energy adaptation, thriving in the radioactive glow of their dead sun. It is a staggering leap of imagination, a biology born not from starlight or hydrothermal vents, but from the aftermath of a stellar explosion. These pulsar worlds remind us that life, if it is truly a universal force, may find a way in conditions we would consider utterly unsurvivable, rewriting the rules of existence in the glare of a cosmic lighthouse. The chemistry of life on Earth is built on a foundation of carbon and water, but what if a world flipped that recipe entirely? There are places in the galaxy where the cosmic scales tip in a different direction, where carbon atoms outnumber oxygen. In these star systems, planets do not form from silicates and iron like our own. They are forged from carbon, giving rise to worlds of astonishing and alien luxury. These are carbon planets, and they might be the diamond mines of the cosmos. Their internal structure would be a geologist's wildest dream. Instead of an iron core, imagine a heart of solid silicon carbide, a material harder than most gems. Above that, immense pressure could crystallize carbon into a mantle of diamond, not in small veins, but in layers hundreds of miles thick. The surface itself would not be rock or soil, but a sticky, gloopy landscape of tars and heavy hydrocarbons, a world where it might literally rain oil. The familiar cycle of water, erosion, and tectonics would be replaced by the slow churn of hydrocarbons, with rivers of methane and ethane cutting valleys through plains of asphalt. In such a place, the very idea of life as we know it dissolves. Water here would be a rarity, probably locked away as steam in a toxic atmosphere or trapped in minerals. But life is opportunistic. If the principle is that a liquid solvent is needed for complex chemistry to occur, this world offers a different one: vast oceans of liquid hydrocarbons. Could life emerge in a sea of methane, using tar and soot as its building blocks? Astrobiologists speculate that on a carbon world, the backbone of biology might not be carbon at all. It could shift to silicon, an element that sits right below carbon on the periodic table and can form similar complex chains. Silicon-based life in a hydrocarbon solvent is a concept that stretches our imagination to the limit. Such organisms would be utterly alien, their metabolisms tuned to consume acetylene or hydrogen, their structures perhaps crystalline or resinous, able to withstand a chemical environment that would be lethal to any Earth creature. They might breathe hydrogen instead of oxygen, exhaling methane. Finding these diamond worlds, however, relies on reading their light. When such a planet passes in front of its star, the starlight filtering through its atmosphere would carry a distinct chemical signature. Our telescopes would hunt for an absence of the usual signs of silicate rocks, like silicon oxide, and instead look for an overabundance of carbon-based molecules, acetylene, methane, and complex hydrocarbons. The spectrum would tell a story of a world rich in carbon and poor in oxygen, a chemical fingerprint of a place where diamonds are common as gravel and the seas are dark, slow-moving pools of organic sludge. These worlds challenge our carbon-based chauvinism. They suggest that the ingredients for life's experiment are not fixed but fluid, shaped by the elemental abundance of their birth cloud. A carbon planet is a reminder that biology might not always seek the path of water and oxygen, but could find a stranger, darker, and more glittering road to complexity. The relentless pull of gravity can forge more than just orbits. It can forge the very warmth of a world. Tidal heating is a cosmic engine, a source of energy born from the gravitational dance between celestial bodies. We have seen its power close to home. Look at Jupiter's moon Io, the most volcanically active world in our solar system. It is not heated by the distant sun, but by the immense gravitational tug of war between Jupiter and its neighboring moons. This constant, rhythmic flexing heats Io's interior to a molten frenzy, erupting in plumes of sulfur that paint its surface in garish yellows and reds. That same process, gentler and deeper, is what keeps the global ocean of Europa liquid beneath its icy crust. This tells us something profound. A planet does not need to be in the Goldilocks zone of its star to be warm. It simply needs to be in a gravitational embrace. Now, take this concept and cast it across the galaxy. Around red dwarf stars, where planets are often packed tightly together in close orbits, tidal heating could be a dominant force. In these cramped systems, the gravitational interactions are intense and constant. Planets can become locked in orbital resonances, a precise rhythmic pattern where their gravitational nudges reinforce each other, like pushing a child on a swing in perfect time. This sustained pushing and pulling flexes the very rock of these worlds, generating immense internal heat from friction. The result could be a planet far outside the traditional habitable zone, a frozen snowball in terms of starlight, yet glowing with geothermal warmth from within. Its surface might be a global ice shell, but beneath that, a tidally heated ocean could churn, kept liquid by the gravitational music of its planetary siblings. The implications are staggering. It means the true habitable zone of a star system is not a simple, thin ring. It is a complex, three-dimensional web of gravitational relationships. A world that appears too cold on a chart could be a geothermal powerhouse, its hidden sea sustained by the invisible pull of its neighbors. We can picture these systems through animation, watching as planets swing past each other, their gravity wells deforming one another, sending waves of heat pulsing through their cores. This internal furnace could drive volcanic activity, replenish atmospheres, and most importantly, maintain those subsurface oceans that we now see as universal havens for life. The search for life therefore expands dramatically. We must look not just at a planet's distance from its sun, but at its cosmic dance card, at the intricate gravitational ballet it performs with every other body in its system. A lonely, quiet orbit might mean a cold, dead world, but a world in a dynamic, resonant system could be alive with inner fire, carrying its own warmth into the eternal night. Our own solar system holds a frozen frontier far beyond the familiar planets, a place so distant and dark it defies easy comprehension. This is the Oort cloud, a vast, spherical shell of icy remnants left over from the solar system's birth, extending nearly halfway to the nearest star. It is a cosmic deep freeze, a graveyard of primordial material where trillions of comet nuclei drift in a slow, silent orbit around our sun. These are not just dirty snowballs, but complex worlds in miniature, composed of water ice, frozen gases, and rich organic compounds. For most, the cold is absolute and unending. Yet, for some of the larger bodies, there is a potential source of warmth from within. Radioactive elements like aluminum-26 and iron-60, isotopes that were present in the early solar nebula, could be embedded in their rocky cores. As these elements decay, they release heat, a faint, persistent glow that could last for billions of years. If an Oort cloud object is sizable enough, this internal warmth might be sufficient to melt a deep reservoir of ice, creating a pocket of liquid water, a subsurface ocean sealed beneath a thick, insulating crust of primordial ice. It is a profound thought that in the absolute dark at the edge of our own home system, hidden oceans could persist, tiny, isolated biospheres cut off from the sun's light for the entire history of our solar system. This concept shatters the boundary of our system entirely when we consider the visitors that pass through it. In 2017, our telescopes detected an object unlike any other, a dark, reddish visitor tumbling through our solar system at a staggering speed. Its trajectory was clear. It was not from here. We named it Oumuamua, a Hawaiian word for scout. Its elongated shape and curious acceleration sparked endless debate. Was it a bizarre asteroid, a fragment of a shredded planet, or something else entirely? Then, in 2019, we spotted a second visitor, 2I/Borisov, which revealed itself as a clearly icy comet, ejecting gas and dust as it rounded the sun. These were our first confirmed interstellar objects, pieces of other star systems passing through our cosmic neighborhood. Their existence opens a breathtaking possibility. What if these travelers are not just barren rocks or simple comets? What if they are fragments of shattered ocean worlds, pieces of Hycean planets or icy moons that were blown apart by cataclysmic collisions in their home systems? Such fragments could be more than just inert rubble. They could be cosmic arcs carrying within their frozen hearts the very building blocks of life, complex organic molecules, and even pockets of salty water, preserved in the deep freeze of interstellar space. Could dormant life itself, in the form of extremophile microbes frozen in stasis, hitch a ride on such a journey? The theory of panspermia suggests life could be spread between star systems by just such mechanisms. A microbe deeply embedded in the ice of a fragment from a once habitable moon could survive the radiation and cold of an interstellar voyage lasting millions of years. When that fragment eventually crashes into a young, wet world in a new system, it could seed that planet with the precursors of life or even life itself. Oumuamua and Borisov may have been sterile messengers, but their mere passage proves the galaxy is constantly exchanging material. Ice and rock, the ingredients of worlds, are forever on the move. This means the story of life's origins on Earth may not be a local tale. It could be a galactic epic written across light years and delivered to our doorstep by silent, frozen couriers from the depths of time and space. The ultimate sign of intelligence might not be a radio signal, but a star that begins to vanish. For a civilization that has mastered its planet and yearns for more, the energy of its sun becomes the ultimate prize. This leads to a concept that stretches the limits of engineering, the Dyson sphere. Proposed by physicist Freeman Dyson, it is not necessarily a single, solid shell, but more likely a vast swarm of orbiting solar collectors, millions of individual satellites or habitats encircling a star to capture nearly all of its light. This megastructure would be the defining project of a species that has truly graduated to a galactic scale, harnessing power on a level we can barely comprehend. But such a civilization cannot hide the physics of its ambition. A star wrapped in a Dyson swarm would present a bizarre and unmistakable signature to our telescopes. From the outside, the star itself would appear to dim dramatically, or even flicker in strange, unnatural patterns as the collectors move in their orbits. More tellingly, all that captured stellar energy has to go somewhere. It gets used, and eventually it is radiated away as waste heat in the form of infrared light. So astronomers searching for these constructs don't just look for missing starlight, they scan the heavens for unexplained, massive sources of infrared radiation, the thermal glow of a civilization's ultimate power grid. This shifts the entire search for alien life into a new realm. We are no longer just hunting for the chemical signatures of microbes or algae. We are searching for technosignatures, the detectable evidence of advanced technology. A Dyson sphere is just one possibility, perhaps the grandest. Others are more subtle but equally revolutionary. Imagine a powerful, focused laser beam used for interstellar communication, flashing a coded pulse across the light years. Or consider the atmospheric pollution of an industrial world. On Earth, we release chlorofluorocarbons, artificial compounds that do not occur naturally. If our telescopes detected similar molecules in the atmosphere of an exoplanet, it would be a strong indicator of an active technological society. Even the glow of a planet's night side could betray a presence. A world covered in city lights would have a distinct, artificial brightness when its dark face is turned toward us, a global testament to a species that has conquered the night. This search requires us to look with new eyes. We must analyze the data from our telescopes not just for the gentle curves of natural worlds, but for the sharp, unnatural angles of megastructures, the unexpected spikes of laser light, or the chemical fingerprints of industry hanging in an alien sky. It is a hunt for the architects, for those who have looked at their sun and seen not just a source of life, but a source of power, and who have reached out to take it. But the most extreme source of energy in the cosmos is not a star. At the heart of nearly every galaxy, including our own Milky Way, lies a supermassive black hole, a gravitational abyss with the mass of millions or even billions of suns. This is the galactic core, a region of unimaginable violence and brilliance. The immediate edge of the black hole, the event horizon, is a point of no return. Yet, just beyond that point of infinite darkness, something spectacular happens. As vast clouds of gas and dust are pulled inward by the titanic gravity, they do not simply vanish. They spiral into a flat, superheated disk called an accretion disk, moving at nearly the speed of light. The friction and magnetic forces within this disk are so intense that it glows with the light of 1,000,000,000,000 stars, a beacon of ferocious energy that can outshine every star in its host galaxy combined. It is the most luminous engine in the universe. For any conventional world, this environment is a death sentence, scoured by lethal radiation and gravitational tides that would shred a planet. But what if a planet orbited a normal star that itself circled at a very specific, safe distance from the chaos? At a certain range, the incredible flood of light and heat from the accretion disk and the densely packed stars of the galactic core could provide a stable, eternal source of warmth. A planet in such an orbit would have no need for a sun of its own. It would be bathed in the perpetual, radiant glow of the galaxy's central engine. Its sky would be a breathtaking spectacle, a swirl of brilliant stars and the shimmering, multicolored ring of the accretion disk dominating the heavens. Life here would exist under an alien sun that is not a sun at all, but the glow of doomed matter circling an infinite dark. This scenario introduces one of the most mind-bending consequences of a black hole's gravity, time dilation. As portrayed in films like Interstellar, gravity warps time itself. The closer you are to a massive object like a black hole, the slower time passes relative to the rest of the universe. For a planet orbiting at a safe but significant distance, time might flow only slightly slower. But for a hypothetical advanced civilization, this could be a tool. A research outpost placed closer to the event horizon could experience years while millennia pass in the wider galaxy, allowing for the slow, patient study of cosmic evolution or the execution of projects that span eons. Conversely, a civilization might place its long-term archives or hibernating populations in such a time-slowed zone, preserving them for a distant future. Could a species not only survive in this radiant maelstrom, but thrive by harnessing it? The concept stretches our imagination. A civilization capable of engineering here would have mastered energy on a scale we can scarcely dream. They might build colossal solar collectors, not around a star, but facing the accretion disk, soaking up its immense power. Their technology would have to be resilient beyond belief, hardened against intense radiation and gravitational stresses. For them, the black hole would not be a menace, but the ultimate power plant, the furnace at the heart of their world. It is a staggering vision of adaptation, where life finds a way not in the gentle light of a star, but in the radiant fury of the universe's most destructive force. The story of life does not begin on a planet. It begins in the cold, dark emptiness between the stars. Before a single cell could divide, before oceans could pool, the universe had to assemble the raw ingredients. For decades, we believed these building blocks were forged solely on young, wet worlds, but a series of stunning discoveries has rewritten that story. We now know that the chemical seeds of life are sown in the vast, diffuse clouds of gas and dust known as nebulae. In these cosmic nurseries, amid the faint glow of starlight and the whisper of solar winds, chemistry is hard at work. Using powerful radio telescopes, astronomers have performed a kind of remote spectroscopy, analyzing the specific wavelengths of light absorbed by these clouds. The resulting data graphs reveal not just simple atoms, but the distinct, jagged signatures of complex organic molecules. They have identified amino acids, the very units that link together to form proteins in every living thing on Earth. They have found sugars like glycolaldehyde, which is a component of ribose, the backbone of RNA. They have detected alcohols, acids, and ring-shaped molecules called polycyclic aromatic hydrocarbons. These are not just random chemicals, they are the precise molecular pieces required to build the machinery of life. This is probiotic chemistry, the set of reactions that create life's precursors, and it is happening on a galactic scale in the void. How is this possible? In the near-perfect vacuum of a nebula, individual atoms and simple molecules drift endlessly. But when they stick to the surface of microscopic dust grains, floating like cosmic snowflakes, everything changes. These dust grains act as tiny chemical laboratories. On their frigid surfaces, atoms can meet and link together, shielded from harsh radiation. Over millions of years, simple molecules like carbon monoxide and water ice are transformed by the gentle energy of starlight into more complex structures. Eventually, these coated grains clump together into comets and asteroids. When these icy bodies later crash into a young, warm planet like the early Earth, they deliver a rich cargo of pre-made organic material. It is a cosmic delivery service raining down the starter kit for biology. The evidence is painted across the sky. Look at the Orion Nebula, a brilliant stellar factory visible even through binoculars. Its swirling colors are not just pretty gas, they are a chemical soup. The red hues indicate energized hydrogen, while the blues and greens trace the presence of oxygen and other elements. Within those clouds, the data tells us the same amino acids found in meteorites on Earth are being synthesized right now. Animations help us visualize this invisible process, showing how atoms link on dust grains, forming chains and rings that eventually detach to float freely. This changes everything. It means the universe seems almost pre-programmed for the chemistry of life. Wherever you have carbon, hydrogen, oxygen, and nitrogen stirred by starlight and given time, these fundamental reactions appear to follow. The path from nebula to cell may not be a miraculous accident, but a natural progression written into the laws of physics and chemistry. We are not separate from the cosmos, we are a product of its most fundamental tendencies. The molecules in your body, the ones that allow you to think and feel and wonder about the stars, were forged in the hearts of ancient suns and assembled in the dark clouds between them. We are, in the most literal sense, stardust that has learned to look back and wonder where it came from. The chemical whispers from a nebula must find a home, and that home is the air a world breathes. Our search for life has now reached its most critical and delicate phase, moving from identifying promising places to analyzing the very atmospheres of distant worlds. This is the frontier of detection, where a planet's thin, glowing shroud of gas becomes a cosmic laboratory, and our telescopes become the most sensitive chemical analyzers ever built. The James Webb Space Telescope is our primary instrument in this new era. It does not take pretty pictures of these exoplanets. They are far too distant and drowned in the glare of their stars. Instead, it uses a powerful technique called transmission spectroscopy. Here is how it works. When an exoplanet passes directly in front of its star from our point of view, a tiny fraction of the star's light filters through the planet's atmospheric rim before reaching our telescopes. Different gases in that atmosphere absorb specific colors or wavelengths of that starlight. By splitting that filtered light into a detailed rainbow, a spectrum, scientists can read the missing colors like a barcode. Each dip in the graph corresponds to a specific molecule. It is a fingerprint of another world's air. The data arrives not as an image but as a graph, a line that dances and dips across a grid. A flat line would mean a barren, airless world or one with a perfectly uniform haze, but a graph with a forest of dips and valleys tells a story of a complex, dynamic atmosphere. We compare this to a reference spectrum of Earth's atmosphere taken from space. Our own graph shows the profound signatures of life, the deep valleys of oxygen and the smaller, telling dips of methane and water vapor. The key is to look for combinations, for gases that should not coexist for long unless something is constantly replenishing them. Oxygen is a powerful biosignature because it is highly reactive. On Earth, our abundant free oxygen is almost entirely a product of photosynthesis, pumped out by plants, algae, and cyanobacteria for billions of years. Without life, oxygen would quickly vanish, binding with rocks and gases. Finding oxygen alone is intriguing, but finding it alongside methane is a much stronger signal. In a planetary atmosphere, methane and oxygen react and destroy each other. To see both in significant quantities means something must be producing them rapidly and continuously. On Earth, that something is life. Other potential biosignature gases include nitrous oxide, produced by microbial processes in soil and oceans, and of course phosphine, which sparked the debate about Venus. But a single gas is never proof. The true art of this science is context. We must become cosmic detectives, ruling out false positives. For example, a planet with extreme volcanic activity could pump out gases that mimic biological ones. A water world undergoing intense photolysis where starlight breaks apart water molecules could build up oxygen abiotically. This is why we need more than a snapshot. We need to understand the planet itself. Is it a rocky world in the habitable zone? Does it show signs of liquid water or a global ocean? Does it have a protective magnetic field? The atmospheric spectrum is the final, crucial piece of evidence, but it must fit into a larger puzzle of habitability. Future telescopes, like the planned Habitable Worlds Observatory, will take this even further. They will be designed to directly image Earth-sized planets, blocking out the blinding light of their stars to capture the faint blue dot of a world itself. Then they will analyze its light for the reflected signature of continents and oceans, and the atmospheric spectra for those telltale signs. We are learning to read the stories written in alien air, searching for the chemical sentences that spell out one simple, universe-changing word: life. All these wonders, all these possibilities, lead us to a profound and haunting silence. The universe is unimaginably old, over 13.8 billion years old, and staggeringly vast, with hundreds of billions of galaxies, each containing hundreds of billions of stars. Given the sheer number of opportunities and the cosmic chemistry that seems to favor life's ingredients, the galaxy should be teeming with intelligence. The physicist Enrico Fermi, over a lunchtime conversation, captured this contradiction with a simple, devastating question: where is everybody? This is the Fermi paradox. If life is a natural cosmic process, then advanced civilizations should have arisen long before us, and their presence should be obvious across the stars. Yet we look out and hear only silence, see only empty space. The 25 cosmic wonders we have explored are not just destinations, they are potential answers to this great silence. Perhaps life is indeed common, flourishing in the hidden oceans of icy moons and the steamy atmospheres of Hycean worlds, but intelligence is a rare and fragile fluke. Evolution may frequently produce microbes and algae, but the leap to self-aware, technology-building beings might require such a specific and unlikely series of events that we are truly alone in our curiosity. Or maybe intelligence is common, but it is fleeting. Civilizations may inevitably reach a point where they destroy themselves with their own technology, through war, environmental collapse, or runaway artificial intelligence. The window for a species to broadcast its presence into the galaxy might be tragically short, a brief flash in the cosmic dark before the silence returns. There are more optimistic possibilities. Advanced civilizations might not be hiding. They might simply be invisible to our current methods. They could have transcended physical forms, uploading their consciousness into virtual realities or merging with their technology in ways that leave no radio signals or atmospheric pollution for us to detect. Their engineering might be so advanced it appears as natural phenomena, their Dyson swarms indistinguishable from dust clouds around young stars, or they might be observing us under a strict principle of non-interference, a galactic quarantine until we mature as a species. Our search among these 25 wonders is an active test of these hypotheses. Every time we point a telescope at the atmosphere of an exoplanet like K218b, we are asking if life is a chemical inevitability. Every mission we plan to drill into the ice of Europa, we are probing the idea that life is common but hidden, thriving in subsurface darkness. The empty spaces between the stars, the ancient light from galaxies that have had billions of years more than our own to foster intelligence, that very emptiness is data. It tells us that something is filtering the rise of visible galactic civilizations. Our journey through these cosmic wonders is more than a tour of potential homes. It is a grand experiment to understand our place in the story of the universe. Are we a miraculous accident, a lonely voice in an empty cathedral? Or are we simply newcomers, late to a conversation that has been flowing in forms we are only beginning to learn how to see? The silence is not an end, but a question written in starlight, and we are just starting to learn how to listen. That profound silence from the stars makes the vibrant, noisy reality of our own world all the more astonishing. After a journey spanning hidden oceans and alien suns, we arrive at the final and only proven cosmic wonder on our list, Earth itself. This pale blue dot is not just our home, it is the single data point in our search, the one place we know for certain the experiment of life has succeeded. Every extreme environment we have imagined elsewhere exists right here, and life has found a way to thrive. In the crushing, sunless depths of our oceans, entire ecosystems cluster around hydrothermal vents where microbes convert volcanic chemicals into energy, supporting towering tube worms and ghostly crabs. In the acidic, toxic waters of Rio Tinto in Spain, or in Chile's otherworldly Atacama Desert, where rain may not fall for decades, resilient bacteria persist within the very rocks. In frozen lakes buried deep under Antarctic ice, isolated for millions of years, unknown microbial communities survive in the dark and cold. These are not just curiosities, they are living proof of life's incredible tenacity, a field guide to what might be possible on Europa, Enceladus, or a distant Hycean world. By studying the limits of life on Earth, we are writing the manual for how to recognize it elsewhere. Our planet is a kaleidoscope of biospheres, each a testament to adaptation. This incredible diversity is our greatest tool. When we analyze the chemical signature of Earth's atmosphere from space, we see the unmistakable fingerprint of a living world, a complex mix of oxygen, methane, and water vapor that would baffle any alien observer looking our way. That same fingerprint is what we now search for in the light of distant stars. So, as we gaze at breathtaking views of our planet from orbit, the swirling whites of clouds over deep blue seas, the green tapestry of continents, and the fragile glow of city lights in the night, we are looking at more than just home. We are looking at a cosmic wonder in its own right, a laboratory, an ark, and a beacon. It grounds all our speculation in known science. Every strange, hopeful world we have explored is a reflection of a possibility first demonstrated here. The search for alien life begins with a deep appreciation for the alien life already among us, in our deepest seas and highest mountains, showing us that life, once it takes hold, clings with a ferocious and beautiful will to exist. Our planet is the first chapter in a story we are only beginning to read, and its lesson is clear: where there is energy, chemistry, and a little liquid water, life finds a way. That truth, discovered here, is the hope we carry to the stars. Our journey has swept us from the frozen crust of Europa to the steamy skies of Venus, from the diamond hearts of carbon planets to the silent, drifting arcs of the Oort cloud. We have stood in the twilight of tidally locked worlds and imagined life floating in the eternal glow of a galactic core. This epic tour reveals a fundamental truth about our search. We are not merely hunting for a second Earth, a pale blue dot in a distant sky. We are searching for life as we do not know it. We are preparing to meet biology that breathes hydrogen, thrives in sulfuric acid clouds, or harvests energy from the radioactive decay of a pulsar's fury. The universe is not a sterile gallery of rocks and gas. It is a workshop of infinite chemical experiments, and on countless benches, the experiment of life may be running in forms our earth-bound minds have yet to conceive. This is why the silence of the cosmos is not empty, it is pregnant with possibility. Every unanswered signal, every unexplained atmospheric signature, is an invitation to look deeper, to think broader, to wonder more wildly. So keep looking up. Let your curiosity be the compass that points past the familiar stars. Wonder about the dark oceans under alien ice and the creatures that might swim in absolute blackness. Wonder about the civilizations that may have mastered time itself near a black hole, or the simple, resilient microbes that could be raining down on us from interstellar space right now. This story belongs to all of us. Tell us in the comments which of these 25 cosmic wonders do you believe is the most compelling home for alien life. Is it the hidden sea of Enceladus, the hydrocarbon rivers of Titan, or the ancient, patient oceans of a rogue planet drifting between the stars? Share your vision of where we should look next. And if you want to join more journeys to the edge of understanding, to unravel the mysteries of black holes, ancient civilizations, and the fabric of reality itself, be sure to subscribe. The universe is waiting, and its greatest wonders are still